Good morning, everybody. We are back with day 12 of Advent of Code 2022. As you may have noticed, there was not a video yesterday. I recorded several hours of video. I got the first part of day 11 done in about an hour, not too bad. But I'm still stuck on the second part, so no video for day 11 just yet. um, but we're going to keep moving on with day 12. Today, again, part one doesn't look so bad. It looks like we're just going to be doing a tree search over a grid like this. So let's give that a try. And we're going to use our tree from day 7. We're going to try to make it a little more generic. I think the tree we wrote that day, I didn't want to make that tree or move that tree into our Advent 22 library because it seemed like kind of specific towards this, but today's going to be more of a generic tree that I think will actually be able to factor out into its own little library. Anyway, let's go ahead and get started. So we'll do our classic load sample for line and s.lines. What are we going to do with the line? Basically, we're going to break it into characters. We're going to convert those characters into numbers because each of these is an elevation, actually. I did think about leaving them as characters, which would be fine for comparisons, but we need to do the kind of comparison where we check if it's at most one higher, not just like less than, greater than. If it were just relative comparisons, it would be fine to leave them as characters, but I think we'll actually want these numbers to be numbers. Okay. For line in s.lines, we're going to have to know the starting position, but we'll figure that out in a second. For now, let's do line.chars dot map, and I've got to turn that off. Well, let's call it C because it's a char, and we're going to say to height on C. Let's see, we need to do something different in this case though. If C equals S, to do, well, that's going to fail immediately. Else if C equals E, to do, and then we do just return that. And I think we'll go ahead and collect that. We'll say let V equal this will be the vec, and let grid equal vec new. So once we've collected that, we'll just do grid.pushV. Let mute grid, obviously. And we need to define to height. So we'll make fn to height C char. It's going to return a usize, because why not? And I think the easiest thing to do is we're basically just going to take A to Z, and I think we can zip that with 0 to 26. Dot collect. I think we can collect that into a hash map. Of course, equals hash map of char to usize. And then we just look it up in the map of C. Great. To height C. Alright, so this is obviously going to panic immediately, but let's give it a try anyway. Debug grid. We'll run it. It says to do line 18 because S is the first character. Yeah. So S is also 0, but we need to note down where it is, basically. So I think maybe, we'll just enumerate in both places. So this will be JC. Can I just 2D J? No. Alright, and then we'll do I lines. This is a row. S dot lines dot enumerate. So if this is the case, then we will set let mute start equals 0, 0, which it actually will end up being kind of funny. But we'll set start equals ij and end also start there, and then we'll set the end to ij here. Great. So debug grid I and wow, lost control for a second. ij. Oh, start end. Woof. No entry found for key. Oh right, this is supposed to be else. Because this needs to return 0 and this returns 26, 25. Excellent. Okay. 1, I guess Q is a 16th letter, 15. Okay, this looks reasonable to me. Hopefully that's correct. Yeah, start 0, 0, and then let's see, 0, 1, 2, 0, 1, 2, 3, 4, 5 is the end. Okay, great. So we've got our grid collected. Now, we need our tree. So that's how we load. We got 2 height. Of course, this should be lazy static or something. We don't need to do this every time we call the function. But I don't want to import lazy static or one cell just for that. Great. Let's go look at day 7 and try to borrow our tree. So file tree. I'm going to leave off the comment. I feel a little bit bad, but it's okay. How much of this do we have to copy? Let's see, we need file tree, which has the arena, the nodes here, the current, we actually don't even need like the current position, I think. Yeah, this is just like totally different. But let's just copy, we'll copy it all for now, and we'll prune our tree instead of trying to grow it later. Alright, so let's go over here. Put this at the top. So clearly we don't really need that. Yeah, it seems we don't need those really. Okay, so I believe this is supposed to be a node actually. A node with an optional parent, and then it contains some kind of data. So this is where we're supposed to make it generic, I think. Okay, we can do this, I guess. Node T, where this is just data. It contains some kind of data. Datum. This is node T. So this is generic T. Let's change the name of this to just tree. And I think we'll get rid of cur. Alright, impl. Do we have any restrictions on T yet? I don't think so. Oh, I should have. Okay, so type is supposed to be data. We don't. No, let's get rid of all of this. Yeah, cd add file meaningless to us. Great. And yeah, file type we can get rid of. So we've got nodes, we've got trees. What operations are we going to have on trees? Well, we need push. I know we need push. And then eventually we're going to have to be able to lock it. So really we should impl iterator probably, but we'll see. Okay, vec node t, a tree. Beautiful. Oh, I did copy the comment. Okay, so we're loading our tree here. Grid, start, end. Let's keep things factored a little bit today. We'll call this load grid. I do like to put my main at the bottom. I wish I wouldn't always put it up there. Oh, complex type. No. Stupid Clippy. Alright, we can say type grid is a vec u size. Wow, do you feel better now, Clippy? Great. Okay, so we've loaded our grid. That should be good. Let's collapse that. Now, load sample, load grid. We need to walk our grid. So for row and grid, for call and row, we need to, basically, yeah, so what I'm going to do with this tree, we're going to do a, let's see. Well, I guess we're not even doing the search yet. I keep wanting to say, like, we're going to do a breadth first search, but, or a depth first search. But I guess the point is we're going to build a tree, and then we'll traverse the tree. Probably you could do it in one pass, but that seems difficult. I guess it's not really difficult. This path reaches the goal. No, it's not, because we're not scoring the steps. Okay. Is this even a tree? I think it's a tree. Because, yeah, you've got multiple decisions. I mean, it's a lot. I read a book on, it's called How Computers Play Chess. Not one of my favorite books, I'm sorry to say, but they talked a lot about tree searches, and this feels like exactly the same thing, right? Like, at every step, you know, you make a move, and the tree, yeah. I mean, it's clearly a tree, I think. Anyway, so actually, we're going to be starting at the starting position. Okay. Yeah, maybe we're not just looping over the grid. We start at the starting position, and then we need to, yeah, I mean, I think the structure is going to be a lot like a chess engine, right? Like, we'll have something, we can have generate moves that takes the current position, yeah, sure, let's say type point is a u size. And it takes a grid. And it returns a list of points. Generate moves. Legal moves, of course. This sounds just like a chess engine. Generate legal moves. And then we will search for all of the paths through the tree that terminate. Yeah. Okay. So no, stop this. All right. First, we build tree of legal moves at every position. Then find paths through tree terminating at end. Choose the shortest one. Great. Okay, so our initial position is start, obviously. Okay, generate moves. Yes. So alright, there's going to be recursion here, of course. Because how do we generate moves for a point? I don't think this return is correct. Generate moves. Well, maybe it's correct. We'll see. We'll see. So basically, we call generate moves at the start with grid. Alright, so let's say moves. Now let's just debug moves for now. So let's see what we should be able to do at the start. So at the start, it looks like we could go to A or A. We can go up or down. During each step, you can move one square up, down, left, or right. Okay, so generate moves at its most basic. Let's let x, y equal pause. We need to look up, down, left, right, and then check if the height is at most one higher than our current square. All right, and then we'll let h be grid of x, y. Good, good. Why don't, let's make this an actual, whoops. No. Struct grid. We still need that. And then we can impl index usize for grid. Output is usize, and we can do this here, like xy equal index. We return self.0 x, y. Great. And now we can actually do grid of pause. Great. Beautiful. Much nicer. Okay, so to generate moves, again, we look up, down, left, right. If x is greater than 0, then we can look left. Okay, I guess we'll have let me ret equal that new. Okay, so if it's greater than 0, that means we can look left. So let's try let h2 equal grid of x minus 1, y. If h2, alright, just put a to do down here so it stops complaining. If h2 at most one higher is less than or equal to h plus 1, then ret.push x minus 1y. Now, while we're in this, if x greater than 0, we can, oh no, there's no diagonals. There's no diagonals. Okay, so x greater than 0. If y greater than 0, then we can do y minus 1. Okay, and then we have to look at the other extremes. And if y less than, it would be nice if we could give, alright, let's have an impl grid, fn shape self returns a... See, this one's not really a point. So this is going to return self.length of self.0.length. That's the number of rows. And self.0 of 0.length. So obviously it panics if the grid is empty, but that's okay. And now here we can say let mx, my equal grid.shape. If y less than mx minus 1, then we can do y plus 1. And something similar for x. If, oh, this should be my, and this should be mx. Then this should be x plus 1, y, x plus 1, y. Great. And then we just return rect. Beautiful. So let's debug moves. So we could, from the starting position, we could move to 1, 0 or 0, 1. And that's correct. Great. Okay, generate move, start grid. Okay. Now, I think this is actually, I think generate moves should be the one that recurses. Like this should return, so it returns a position, and we always use the same grid. So we can keep calling generate moves, and then we don't want this to return a vec point. We want it to return one of our trees, actually. So we just need to figure out how to push these into a tree. Okay. Yeah. I think that's right. Okay, generate moves. A tree. How does recursion work with the kind of tree we have? That seems a bit suspicious. Maybe not. Maybe we just loop. Maybe we can just do it with a loop. So these are the initial moves. Yeah. Let's see. Generate moves. Because let's see. Because we get these moves, then we want to call generate moves again on these moves, right? And we want to repeat that until we stop finding additional moves, basically. Until we reach the end, or that's funny, left fringe. Yeah, until we reach the end, until we stop generating moves. But then we should also be able to specify if we stop generating moves because we reach the end, or we just got stuck. Now, I guess this should be... I guess you actually do want depth for... No. Breadth for search in this case, because we're looking for the shortest route. Maybe that's not true. I mean, yeah. I've never taken computer science classes. Probably there is some reason for both. Let's see. This path reaches the goal in 31 steps, as few as possible. Okay. I feel like the second part two to this might just be counting all possible paths. So if we do this with this tree implementation, we'll be able to count all the paths. So anyway, generate moves. Let's think about this. We got to think about recursion again. Generate moves. So yeah, this just needs to return a tree actually. Because how do you generate moves? Well, we'll change the name. It'll be like generate path maybe. Yeah, you give it a point. It looks for the moves for that point. But we can't find the rest of the path without calling it on that. Yeah. Okay. So I think this actually needs to take not just a point, it needs to take a node. We're going to be cloning this guy all over the place. This might be, we might use an RC on the grid. Let's see. Okay. Yeah. Write that push. Okay, so this push, I think, is wrong. Write that push. Yeah. Alright, so this needs to be a tree. This takes a tree and returns a tree. Takes a tree, returns a tree. Takes a tree, returns a tree. So this needs to be, takes a tree of... I guess we'll call it a tree at point, right? And it returns a tree at point. That way we can recurse. Okay. Yeah, wait, how do you... Maybe it just... No, it takes... I guess it takes a point? Oh my goodness. Why? I find this so confusing. Alright, maybe we can forget the tree for a second. So generate moves. Build tree, leave moves. Yeah, okay, maybe we can build the tree up one level at a time. Let's try that. So let's make a new tree. So tree impl tree. Okay, let's have fn new. Turns a self. It's just self of nodes. Vec new. Tree new. Okay, how do we push something into a tree? That's a good question. So I guess that's why we had that notion of a current position before. Operations. Enumerating, searching for an item, adding a new item, add a position. Yeah, okay, so I guess insert, tree insert just has a, it takes a position. Now, how do we denote the position? Is a good question. We might be able to get away with... Yeah, it's just kind of difficult here. Walking the tree. Often an operation might be performed. I guess actually, if our nodes are holding points, they will actually be unique. I think that's not true because multiple Yeah, multiple. There. This is like a graph, not just a tree, right? Because it can be like there can be loops and stuff. Yeah, not a tree. Oh my. Oh no, we can have cycle. Oh no. Surely they haven't done that to us, right? Yeah, because I think there are multiple ways you can get to each position. Let's see, A, B, C. Yeah, you could also do A, B, C. So that's like a cycle right there. Oh man, you guys probably aren't going to see this video either. Insert at the current position. Yeah, what if we just insert? We always insert at the current position. Let's get rid of the tree. Just forget about the tree for now. Okay. Generate moves. Yeah, okay. Alright. I think we will just call this in a loop until we find the end. Generate moves. Alright, let's try this. Let mute moves. Loop. For move and moves. Oh, right. Move. For move and moves, if move equals end, break. Yeah, okay, so now I'm going back on what I was saying before. Right now we're going to be in trouble in part 2 because we're not building the tree. But, fine. Fine. Break. And instead of a 4, let's do 4. We'll just say round. Do this again. Well, we can start with 1. That's fine. Break. And maybe we can't do that. Let's just do let mute round equals 1. Round plus equals 1. Move and moves. Into iter. Moves. We're just going to set moves. Yeah, for move and moves. Let you new moves. Back new. And yeah, okay, so we didn't end. So we're going to take new moves dot extend generate moves move grid. And this should also be mutable. Grid. This only needs a reference to a grid. And this also needs a reference to a grid. Oh no, yeah, I had this messed up. This does not need to be mutable. Oh, I guess we can take this. We can just take moves, and then at the end of the loop, we will set moves equal new moves. I mean, we don't have to take this. This is kind of silly. This is unreachable. I hope not. Oh, yes, tick outer. Break outer. Great. Debug round. Speculative. Infinite loop. Okay, well that's not good. Why is that? Why is that? Oh, wow. Okay. Alright, well, I think I'm going to go ahead and, yeah. I'm probably going to call the video there, because this looks like another thing I don't know how to do. Yep. Yep. Certainly looks like that. This looks like a question of efficient tree search, which I do not know how to do. Wow. Yeah. It's going to be ridiculous. Yeah. That's kind of crazy, actually, that just on the sample, I feel like I've done something wrong here. Because it really shouldn't be that many moves, right? How can there be that many legal moves? How is that even possible? Because on the first, yeah, round is 2. No, round, or on the first round, there are 2 options. So yeah, you start here. You can go here or here. Okay, from here, oh, from here you can go 1, 2, 3. From here you can go 1, 2, 3. So that's 6. That's actually right. Oh man. Yeah. Okay. Yeah. I see. So I mean, recursion doesn't help here. No, this is just insane. I can try running it. We'll try running it in release. Yeah. It's a little faster, but I mean, we have to go, yeah, 19. We have to get to 31. So this is absurd. Okay. Wow. I'm actually shocked that the naive solution can't even handle 4, 5, 6, 7, 8. I guess it's the same size as the chessboard with much simpler moves. Yeah, it's 8 by 8. Wow, I can't even handle the 8 by 8 example. I definitely expected this on the big one, but not here. Not here. Wow. Alright, well, let's try. We can play some tricks maybe with the moves. Um, let's see, x greater than 0. Basically, we'd like to give some preference towards good moves. You know? Oh man, this is just like a chess engine. Generate moves, evaluate moves, or we have to like sort the moves. Oh my goodness. Well, I guess it would be nice, yeah, if we could recurse a little bit. Like you look ahead and we say, um, if any of these moves, like, are they promising, right? And we're not getting rid of any cycles. Like, are there? Let's see. Like, if we get to a dead end, if we get to a dead end, we want to. No, I don't know. I don't know. I'm not wasting hours on this one today. I'm gonna quit early. I'm gonna quit early. Current position to location. Alright. Yeah. I'm gonna call it, I think. Am I on a branch? I meant to go back on the other branch. Um, Alright. Yep, well, you guys won't see this probably, but have a nice day. Alright, I'm resuming the video from earlier. I think I figured out how trees work, so let's give this a try. Let's just rewrite the tree stuff we had earlier. So we're going to have instruct tree. Well, alright, hold on. Let's go back to my undo tree. Oh, it didn't persist. Whoopsies. Alright, anyway, we got instruct a tree. It's going to be generic over T because it holds it has nodes, which is a vec node of T. I think that's it for now. Now, what is a node? We got struct node, generic over T. Data is a T. It has a parent, which is an option usize, which is it has a parent, which is an option usize, which is, that usize is an index into containing tree. None for root of tree. And then it has children, which is a vec usize. Also indices into the containing tree. Okay. So, how do we make a new tree? We're going to have impl tree, impl t, tree, t. And we'll have a new. So, new needs to take, it needs to take a t. So let's call it, I guess we can call it data, t, and it returns a self. So it's going to give us a vec, hold on, self, where nodes is a vector, and it's going to have one thing in it. It's going to have a node, and we can fill that. The parent of the node will be none. Children will be a new vector. And data is data. Okay, so that's how we get a new tree. Now the reason or how I figured this out is I was realizing that when we run this currently, let's go ahead and run this, you'll see how many moves we're getting. What I realized is that each of those moves is, each time we generate moves, we're also generating the previous move. So I was thinking, okay, how do we prevent backtracking, basically? Well, we need to, instead of keeping track of just the current position, we need to remember the whole path we've taken. Okay, so I was thinking, all right, we can have a vector, we just pass around a vector of points instead of points itself. But then I was realizing this is exactly what a tree is. And all we really need to do is just check, we need to make sure that our parent, we're not like pushing our parent to the children. So I think I understand how to do trees now, which is great. Okay, so we got a node. All right, so when we're down here, what we want to do is we're going to have a let tree be tree new, and we're going to pass it our start. And let's go up here. Let's debug. Oh, whoops. Derive debug. And this needs to be debug as well. All right. So let's just debug our tree. Let's comment all of this out for now. Just see what our tree looks like. And we'll allow it use. Just get rid of some of these warnings. You have to put this at the top. Okay. Great. So there is our tree. Now, what we do is we will generate moves. Now we can generate moves on a tree. Okay. And we can actually check. This is good, this is good. Now we need a way to insert. All right. Take this out. Build tree legal moves. Generate moves. Start grid. Now on our tree, let's add a function called head, which just gives us the first element of our tree. Just gives a reference to a node. Okay. Node T. This just gives self dot nodes. Can you do first? And we can unwrap this because the only way you should have a tree is if you called new. We shouldn't have an empty tree. All right. So we can now call moves on tree.head. And yeah, this is fine for this to take a reference to a point. I'm probably going to dereference, yeah, inside. Let's see, let's do X. Give that a shot. Perfect. Oh, yes. X greater than 0. What? How did we lose that one? Tree.head, found struct. Oh, I see. Okay, so when we, let's do impl node, and we'll have, well, this is looking a little silly, but self just returns a reference to a T. Node T self.data. Okay, so generate moves, and in our case, we can just take start. So there's moves. Now for move and moves, For move and moves, what do we do? Generate moves. Maybe generate moves does take a tree. Takes a position. Let's think about this. Let's think about this. It takes a node. Want to make sure it doesn't go back to its parent. Okay, I think this needs to take a tree. Takes a node. This is where it gets confusing for me. So it makes sense for me to generate moves for a node that holds a point. Node of point. Okay. Well, it has to take the whole tree, actually. Yeah, because... Okay, so I think it'd be better to do it out here. Alright, we take a tree. We generate moves at the start. Okay. Let mute new moves. Now, what we're going to do... Let's go back into here for a second. Generate moves. Let mute. Okay, so what we're going to be doing, we generate the moves. Now, we want to go through the moves and look at them. All right, so move in moves. We are going to do tree.push view tree. Well, we need to do an insert. Now, how do we specify the position? I guess it will be we'll do an insert on the head. I guess we need some kind of reference into the tree. Interesting. Yeah, I think, all right, let's try to rethink this. I think generate moves does need to take a tree. Generate moves takes a tree and a position in the tree. That feels right. Let's try tree. Recursion, this sounds a little scary. Let's see. Tree, ref mute tree of point. And position, it has to take because we want to look at node. Maybe it takes, what does it take? Maybe it just takes a U size. U size. Let's try this. Okay, tree of point. So we're going to let pause be tree dot nodes of node dot enter. Okay. So that's our position. Now, I think we want to take ret dot filter dot iter dot filter. We need to check and make sure that the points we're adding are not equal to our parent. So filter p not equal tree.nodes of node.parent. So we actually, let's do this. If let's parent equal this, then we return p not equal parent. tree dot nodes of parent enter, else just false. Dot collect, and that's what we'll return. This should be into iter. And this should be this, maybe? Okay, there we go. But it still returns a vector of points. So it takes a tree just so that we can check the parent. So then it should just take a node. But the thing is, I want this to recurse. Generate points. Yeah, so we're just looking at the node. So yeah, this should actually just take a node of point. And pause is just node. Well, it has to take a reference to the node, for sure. And then this should be node.parent. And then we can get rid of the tree. Oh, no, we do need the tree. Oh, but now it doesn't have to be mutable at least. Okay, so now I can generate moves. It's supposed to take a tree. Start has to be a node. Ah, okay, so we start with tree.head. And grid. So that's how we get our moves. Okay, now we're going to receive our moves, and whatever we passed to generate moves. Okay, let's see. So let cur be, we'll let cur be tree.head. This is cur. Okay, great. So we're going to insert tree.head. I'm not sure. Anyway, when we get these moves, we want to take these moves. Let's see, actually, this might even do it. But we need to push these in. Okay. For move in moves. Generate moves. Tree.hit. We need to update where in the tree we're looking. Update tree. Okay, so when we get these, we want to take cur.children.push move. Oh no, we can't. We have to push into the tree. Tree.nodes.push a node where parent. Okay, this should actually be the index. This is cur, so this is tree.nodes of cur. Tree.nodes of cur. Okay, the parent is cur. Children vec new data is mauve. Let's try that. Try that. Parent is this. Summer. Okay, that seems reasonable. Tree dot. We push a new mode. We push a new node to the tree, and then we need to say tree of cur dot nodes of cur. Yeah, so this type of thing to do encapsulate this in method on tree. Yeah, so this should actually be an insert, I think. Expected U size. Okay. This push. Length. Okay, this is going to be tree push. Children.push. Let L be tree.nodes.length. And we push L. Because usually you'd push L minus 1, but we got L minus 1 by getting L before we added 1. Okay, so this should be a method on tree. We're just going to call this push. And this is going to be tree push. This is ref mute self. It takes a T. So this is self, self, self. And we'll rename, what do you call this? Mauve. We'll just push an item, I guess. I guess we'll call it data. Cur, this should probably be called like index. Okay, so this is tree.push. Tree.push this. Great. Tree.push. And now we need to try tree.push current. So we take cur tree.push current. Okay, I'm trying to see how this works. We need to do this recursively on our tree. Tree.push cur. So yeah, basically we want to set cur to what we just pushed. Maybe this should return the index. Size. Push a node containing, I guess we can do a node containing data into the tree and return its index in the tree. It should return L. Yeah, so now I think cur should be this, maybe. Tree.nodes of cur. Yes. Tree.push this, and then recurse. Let's see, so what's the idea here? is that we're getting moves. Let's take the loop off for now. Let's try to simplify this a little bit. Okay, this look, get rid of new moves, get rid of this. So we generate moves, we push each of those moves into tree.push, and then, so this is all using cur. Okay. This takes tree, tree nodes, cur, and grid. Okay, and let's try recursing, and then we can debug our tree here. Whoops, tree.push. What? Is it not? Oh, we're not getting any moves. Oh, this should be else true. Whoops. Okay, great. There's our tree. It's got 2 children, 1, 0, 0, 1. Great. Great, 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 great. Okay. Now, alright, where's our recursion? We need recursion. Recursion. We're doing trees. Recursion. Generate moves for a node. Yeah, we need to generate moves for a single node. And how do you generate moves for a node? You generate moves for all of its children nodes. Okay, so generate moves should give us the moves for a node. I see, I see. So tree.push, generate moves. Okay, so this should return, actually. So for each move it finds. Oh man, my brain. My brain. This feels very much like the first day, on day 7, when I was trying to write the tree from scratch. I feel like I'm missing one layer of indirection here. Like, we need something. We need the recursive analog of that outer loop we had before. I really want generate moves to return me a node. But no, it has to return a tree. Generate moves. Yeah, maybe it needs to return a tree that we can like merge into the main tree, right? Like, how do we combine 2 trees? This needs to give me a subtree. Okay, generate moves, I think needs to take a tree. Generate moves takes a tree and returns a tree. That sounds right. It takes the root. Yeah, it needs to take the root and return. So we need a base case. The base case is, of course, no legal moves. Well, okay, hold on. Generate moves. Maybe we can do it like this. You generate moves. We loop over the moves. Yeah, maybe this is the loop right here. Okay. And then cur, tree.push, cur. and then yeah, to visit dot push this, and then we don't have to. Well, this doesn't have to be mutable. For move in moves, we'll just take it to visit. We'll take, all right, let mute to visit equal back 0. Loop, let cur be to visit dot pop. Unwrap. So we want to visit, we're going to visit this node to visit dot push, tree dot push. Okay. Now, for move and moves, if move equals end, break, equal 1, plus equals 1. Let's try that. Does that just work? Doesn't look like it. Whoa. Oh. Okay, that doesn't look good. Now, let's see. Loop. Okay, so we're supposed to pop this, generate the moves for that position in the tree, loop over those moves. If we found the end, we break. Tree.push cur move. Tree.push cur move. To visit. So we have to visit the nodes. The issue, I think, is that this isn't really right. Let's see. Okay, next. 0, 1, 0, 0, 3, 4, 0. This is really hard. You can't really visualize this. Generate moves. Okay, we generate moves for the current position. I think, oh man, we need one more loop in here. To visit. Because we really want to visit, we want to visit all of the nodes and move. To visit dot push. Okay, this is making some sense to me. Almost there. Almost there. Maybe this has to be for C in and to visit. Recur into visit. Yeah. We'll just call TVB standard mem. Take ref mute to visit, and this will be TV. We'll take cur, and then we can be pushing to this here, and that will be around. Okay, this is moving. This is like maybe fast enough. No, probably not. 25. It's definitely better than before. Now, I do, if this gets the right answer, after some indeterminate amount of time, I have another idea. So I think instead of this being if let sum, I think it should be while let sum parent. Because we want to search all the way up. Because this is like cycle detection basically. Because right now we're preventing us from going back and forth like this, but we're not preventing something like a cycle, an actual cycle. Well, yeah, I guess right now we're preventing a cycle length 2 or 1, I think 2, because that'd be swapping back and forth between two nodes. We're not preventing any other type of cycle. So let's stop that. Something else we can do. Let now equals standard time instant now. And let's say we can do print line finish round after now dot elapsed dot as millis over 1,000. So now, 0 seconds. 0.4, you see it starts to really slow down. Alright, let's come up here. And what we actually want to do is while let sum parent equal node dot parent. Ooh. Node dot parent is a U size, right? Yeah. No. Let mute parent equal node dot parent. While let sum parent, okay, take out the else. While let sum parent equal parent. If p equals this, return false. And then if we make it all the way out here, it'll be true. So 30 seconds, too long. Let's try this. Uh-oh. This might be an infinite loop. While let sum parent equals parent. Oh, I forgot to update parent. Hold on. Oh. We'll see. We'll call this cur. Cur equals parent. Try that. Nope. What am I doing wrong? Let mute cur be equal node dot parent. While that is sum, shouldn't that be traversing it? 0. Why is while let sum? Why is this happening to me? what is cur? Is an option use size, node parent. So while it's sum, if p is tree.nodes parent.enter. What I'm trying to do is check all of the parents. But it's like I'm not actually updating cur. Why don't I understand this? Okay, let's debug cur here. Cur is none. Yeah, none, none. Sum 0. Okay. So parent should be 0. No, dot parent. This is an option use size. What? So it's 0. Okay, so let's try tree.nodes of parent dot parent. Oh, is this? Oh, that's what I need to do. Cur equal tree.nodes of parent dot parent. That's the issue. There we go. Yes, kill it. Okay. Well, it didn't stop after 31. So we're filtering our points if our point is equal to tree.nodes of parent.enter. So our point is in the list of parents. Then we return false. Otherwise, we say it's true. So what are we returning here? Is my question, I guess. Dot collect 1 0 2 0 1 1 1 1 0 2 2 1 1 2. Well, it's certainly running fast now. Great. Now, why is it not equal to it? What is end? Let's debug end. Whoops. I guess you can't do that. I think you probably... Okay, end is 2.5. And let's debug move, right? Two, 3 2. Oh, I forgot to break outer. This is why you shouldn't allow unused. 31. Oh my goodness, we did it. I think we did it. Yeah, this is why you should turn this off. We need the warnings. Function hit is never used. Fine. Get rid of it. 31. Debug. Okay, I think we did it. 31. Okay. Let's try it. Oh my goodness. Let's see if we can do it. gonna be too slow again, no. Alright, but we did it. We did a tree. I'm pretty excited about that, actually. Let's look at the input. So where's the S? Let's look for S. Big S. Where's the big S? No, I want match case. This is S. Okay, that's S. And let's match E. E's right there. Oh my goodness. So this, so the minimum, I guess, let's start, oh, come on. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, so the absolute minimum is 55 steps. So I'm going to go ahead and say we're not going to get there. Yeah. Okay. So actually, when we get these moves, the thing is, this is a vec of points. We should actually sort them by their height. Yeah. So I think right now we're doing a breadth first search when we really want to be doing a depth first search, something like that. All right. Well, let's log this. Let's try this again on the sample. We get 31. Beautiful. 31 steps. Okay. Past day 12, part 1. Sample, too slow for input. Okay. Yeah, I think the issue is that we are, like I just said, we're doing a breadth first search instead of depth first. So what we would really like to do, because this is to visit, we're just looking at all of the nodes of a given depth. We really want to give priority. Actually, so this, we're filtering loops here. Basically, we would like to sort these I forget what it's called in chess. It's something like progressive deepening. Like, we really only want to consider moves that take us upwards. But if we can't find any moves that go up, then we'll relax to looking at moves that stay the same, that kind of thing. Because right now we're giving every move equal weight. Yeah. Let's also we can take out our timing. Whoops, excuse. We can take out our timing stuff. That'll help a tiny bit. Yeah, we're giving every move equal weight when we really don't want to. So let's try doing some filtering on our moves. So let's see. Let's do, well, we want some notion of our timings, right? Wait, where'd my timing go? Oh, there's the timing. Yeah, let's go back here. Go back here. Let's do this here. Finished, and then we'll just do this. Milliseconds. Let's just do, what can we get? Nanos, maybe? So that's nanos, 1E9. And let's give it to me in scientific notation. 0.2. How about that? 1E9. Okay, so 2.1. Okay, 2.2. So that is 2 times 10 to the minus 3. So it's 2 milliseconds. Wow. Okay, that actually sounds like a long time. Yeah. 2 milliseconds. So we want, let's do some sorting of our moves. Yeah, let's try sorting these. Okay. Yeah, we may not always be able to go higher, right? That's the issue. Let's let current. All right, let's just do this. Moves.filter. Whoops. Moves.into iter dot filter. Well, let's just make sure that compiles. Filter m, and we want to check that. How do we get the height again? Oh, right, grid. We want to say that grid of m greater than equal to grid of curve. Right. Now cur greater than equal to grid of tree dot nodes of cur dot inner, and we can dereference that. And we can dereference that. I see. Let's try that. So 2 milliseconds. All right, that's a bit faster. An order of magnitude faster. Let's see. I highly doubt it. Yeah, not gonna work. No. Still too slow. So that helps. And of course, I mean, there's a chance that this doesn't even work, right? Like, what if we filter everything out? Yeah, and I think if we did strictly greater, probably we won't even get there, right? probably it'll just, yeah, it just never, it loops forever. Yeah. And there is a chance, like, that you have to go down, right? You might have to go down. So this is not really a good idea. Yeah, what would be better, let's undo this. What would be better, like I was saying, is if we could do the depth first. Generate moves. Yeah. Although, at the same time, if you're doing depth first, it seems to me like, how do you know that the first one you find actually, maybe what we should do, yeah, we like to do iterative, is it iterative deepening? Something like that, where we want to search some depth. I don't know. Yeah, I'm not sure if I can get it any better than this. Because this at least keeps us from doing cycles. But the number of nodes is still quite long. Or quite large. Yeah. Well, maybe we can look at TV. Because maybe, I mean, if there are a bunch of duplicates, I don't think there are any duplicates, though. I think it's just monotonically increasing. 56, yeah. Although, did it stop? Oh, it just finished, okay. Are there any duplicates in moves? That could be the case. Yeah, see, that's 0, 2. Okay. Let's try to memoize moves. Because, yeah. Alright. Let mute scene equal hash set new. And every time we get a move, for move and moves, scene dot entry, whoops, scene dot, can you not get an entry in this? Scene dot, if scene dot contains move, then we'll just continue. Probably we have to borrow this. Scene dot insert move. Let's give that a shot. Okay, so that gives us the order of magnitude again. Let's try this. I still don't think that will be enough. Whoa! Oh god, I just pasted in sample. Now I have to wait a minute for that? What did it even say? That's not... I'm surprised it didn't say that, like, that's not even the right thing. 391. Where did I highlight sample? Alright, here we go. At 37 seconds. Let's see. I think Emacs you can set a timer. Set timer. 0, 30 seconds. Okay, alright, we got our timer going. I certainly hope this is the right answer. That would be fantastic. Alright, I'm kind of scared there's going to be like a noise. Oh, nice. Oh, that's the right answer. Okay. Part 2. Oh, now we should find the best starting point. Oh, any squared elevation A. Okay. Okay. That actually doesn't seem that bad. So we load the grid. I think we can delete our timing stuff. Yeah. Extract. Yes. And we can get rid of now. Let's make sure that that still works. 31. Input 391. Great. So now we'll just call that, yeah, RR. We'll just call it find path, I guess. All right. So now we will find okay. Again, I like my main at the bottom. Okay, beautiful. Debug round 31. Let's get this out of the way. So now we need to locate in our grid for row in grid, for call in row, I row in grid, dot iter, dot enumerate, j call in row, dot iter, dot enumerate, let these starts, back new, if call, grid of call. Oh no, if call equals 0, starts dot push call. Oh, push ij. Alright, so we got 0, 0. There are 6 choices. 1, 2, 3, 4, 5, 6. Okay, so now we're going to do starts.iter.map start. Whoops. Dot min. Dot unwrap. Clone. No? Oh, grid. Grid. Start grid. Derive. Clone. Should be fine. Now we don't use start. 29. Okay. Now this one might take a while. Let's do this. Debug starts at length. Starts at length. Find path. 998. Should take maybe 10 seconds. Maybe more. Let's hold off a second. Let's do iter enumerate. Let's try that. Yeah, we have to do this and this. Nope. Oh. This should close. Oh, whoops. There we go. Let's give that a shot. Oh. Whoa. Clearly, some of them are more difficult. Wow. But we should, okay, wait. We can prune this. We can prune this. We can prune it. Okay. And we can give this a max. Max. Actually, we can make max an option use size. Okay. I see. Okay, hold on. Let's turn this back into a for loop. For I start in this. Delete this. Delete this. That should be good. That's all I can. Okay, so for each of these, max. So the maximum number of rounds we need to consider is however many we had before. So let mute end be let mute max be none. The first time we call it, we just give it max. And let r equal this. Max equals sum r. Max. If let sum equals max. If we'll call this old. If r is less than old, max equals sum r. Old. Expected I32. Okay, fine. This can be an I32. Oh. Yeah, I see. Great. Debug max. Okay, max is not used. Max. And delete this. And now we can come into find path. This should still be fine on the sample. Ooh, max is none. What? Oh. Else max is some bar. 29. Okay, so we still get that. We'll leave that in. Now what we want to do is come in here. So where do we do round? Round is out here. If let sum max equals max, if max, well, we can actually do it here, and max is greater than round. Greater than or equal to round, then we just return round. What did it tell me to do? One. That's not right. Debug max. Max is 1. That's not good. Max. Oh, I got this backwards. Round is greater than or equal to max. We return round. 29. There. So now that will prevent us from just running forever, I think. Okay? This is good? 386. And that is less than before? Yes. Yes. That's the right answer. Okay. Whew. We did it. We did it. Thank you all for watching this if you've made it this far. We got our stars. Have a nice day.